So now we go to the next session, which is being chaired by Dr. Onesmus Minyati from the University of Zambia, and the rapporteur is Dr. Sebastian Waita from the University of Nairobi. Dr. Minyati, are you there?
Yes, good morning.
Good morning. And Dr. Waita, are you there?
Yes, good morning, guys.
Good morning. So I hand over the session to the chair and the rapporteur to manage. Thank you very much.
Good morning, everyone. My name is Onesmus Munyati, lecturer, Department of Chemistry at the University of Zambia. I will be the chair for this session. And my rapporteur has already been introduced. Let me just do a check on our presenters. I know that Eva Tito Shana is present. We have Helen Uma. Helen? Miss Helen, University of Nairobi.
Hello?
Yeah, Helen.
Okay, Helen is there.
Helen, I've been talking to her. I think she's been having challenges with her computer, but I see her there. Can she talk?
Yeah, she has responded.
Okay.
Samson, University of Nairobi.
Hello?
Is Samson there?
Samson Jogu.
Hello.
Okay.
I'm not presenting. Yeah? There is a technical issue.
You are not presenting?
Yes.
Judith?
Hello, I'm present.
Oh, Judith is present. Okay, great. Just before we start, I think Eva Shana has requested that she presents last because she is having technical challenges. That means that our first presenter will be Helen. And just to remind you that the presentations are for 15 minutes. The rapporteur is going to remind you when you have 12 minutes. In other words, you are remaining with 3 minutes. You'll be reminded that you're having 3 minutes. So I'm going to request Helen to please prepare to present. You have 15 minutes. Please go ahead.
Thank you. Sorry. Hello?
Yes, please go ahead.
Sorry, the slides I'm seeing are not the ones. I'd sent the updated ones. I request Professor Mwabora to slide show the ones I have updated. I sent early this morning.
Prof. Mwabora, please check that you have the correct presentation, the most recent sent to you.
Please. Okay.
I think, Helen, I'm not seeing.
I think I've gotten them. Let me confirm if they are the ones, sorry. Yeah, I've gotten them. Sorry for that disturbance.
So it's okay.
Are you seeing my slides?
No.
Not yet.
Can you?
Just a minute. I think she's with Mary. And Mary is going to share her screen.
Oh.
Yeah, now we can see them.
Yeah, now we have it. We see it.
Okay.
Slideshow. So put it in slideshow mode. Okay, good.
Okay, is that okay now?
Yes, please.
Okay.
So you can start. Your time starts now.
Thank you very much. I'm Helen Uma, an MSc student at the University of Nairobi, Department of Physics. I'm going to do a presentation on optical properties of selenium, bismuth, tin films deposited by flash evaporation method. And my supervisors are Professor Mwabora from the University of Nairobi and Dr. Muiva from Botswana International University of Science and Technology. On to my first slides. Introduction. We have a challenge with the growth in technology and population. The energy demand is growing day by day. Now, solar energy is the most abundant form of energy, but less utilized. In Africa, we get around 51% of solar energy compared to the other continents. And Kenya in particular, we have far much better placed to utilize, yet it is less utilized. Now, the major issue has been the initial silicon devices that were used. They were very expensive to configure, and also the cost of changing from the silicon wafers to thin film has been a problem. Then from the silicon went to seed CDT amongst others, but they have other challenges of toxicity. Now, there is need to develop thin film photovoltaics that can help ease the problem. They may not 100% be able to overcome the problem, but they can ease the problem. And that is why we decided to study a member of group 6 of the periodic table. Group 5 to 6 periodic table members are semiconductors and photosensitive, hence can be used as photovoltaics. Now in group 6, we have 3 elements, sulfur, selenium, tellurium, which are considered as chalcogenide glasses. They are photosensitive. We chose on selenium. But such chalcogenide glasses have a challenge. They undergo aging very fast. Now, that is why doping is important. And for our case, we chose to dope with bismuth, which improves its photosensitivity and lifetime. And we also thought that doing a ternary thin film is better because it widens the photoresponse range. So we chose tin because tin has a special property of helping to tailor the band gap as well as widening the photoresponse range. There are many methods that have been used for deposition. We chose on flash evaporation method because of its ability to produce contamination-free coatings from composite materials because it is done under vacuum. Now, our main objective was to determine the optical properties of the selenium, bismuth, tin films, and these are the specific objectives to determine the optical constants of the selenium, bismuth, tin films. I've tried to include the percentages at this initial stage so that you can follow my discussion later. Then the second specific objective was to determine the structural properties of the thin film. And the third specific objective, which is the last, of course, is to investigate the effect of bismuth concentration. On to the methodology and sample characterization. After obtaining the 3 powders, okay, we made sure they are of high purity, of course, 99.99%. So after obtaining them, weighing was done according to their atomic percentages. After that, we went into the melt quenching procedure before finally depositing. The experimental procedure has been summarized in those steps given in the diagram. We did the weighing of the powders according to the atomic percentages and put them in ampules, which were thereafter sealed under vacuum. After the sealing process, we did the heating of the ampules in a rocking furnace to assist in thorough mixing up of the components Then the quenching was done. Quenching is done so that we end up getting an amorphous solid alloy. Then after the melt quenching, did the crushing to obtain the powders, followed by cleaning the substrate and finally flash evaporation. Now these are simple setup for flash evaporation. Of course, evaporation is well known to us. It is heating and evaporating. Okay, in this one, the only addition part is the part of dispensing the powder. Here the powder is dispensed. You can see now I'm not able to see my cursor, sorry. Now you can see the label material tube. It is connected to the vibrator. It will dispense the powder so that we have the three components, selenium, bismuth, and tin. Whichever arrives on the hot tungsten board is just evaporated instantly, and this is done in the vacuum. Now, after the deposition process, we went on to measure the transmittance and reflectance of the thin films using the spectrophotometer, which was later followed by analysis of the data with the help of Scout softwares. Scout assisted us to obtain the other constants. Then the plotting of the graphs was done using the Origin software. After obtaining the thin films on our substrate, after doing the spectrophotometer measurements and the running of the data, after having the material, the film on the slides, we carried out surface morphology measurements, and we selected a few thin films because they were actually many. You can't do all of them because of the time challenge. So those few that have displayed on the screen are the one we did for AFM. Then XRD was done for the 120 thin films at 0 and 2 atomic percent bismuth. Then the 220 thin films also was done. So we did the XRD for 3 films. These are the results. Now, this is what we discovered on the AFM photographs. The grain size or the diameter was determined using the intercept method. And it was found to increase with increase in film thickness. Allow me to go to the next slide. Yeah, this is the slide for the 2 films. Comparing the effects of bismuth content. You can see the first one is they are the same thickness, 120 nanometer thick, both of them, but the difference here is the bismuth concentration. The first one, which was at 0% bismuth concentration, the grain size was found to be 3.33 nanometers. And you can see the one that was at 10% atomic bismuth concentration, the grain size was 44.4 nanometers. This clearly indicates that the grain size increases with bismuth concentration. Then the next slide, I've used the same concentration, the same bismuth concentration, 0 atomic percent bismuth concentration, and I've changed the thickness. The first one, the one to the left, is the 120 nanometer thin film. The second one is 220 nanometer thin film. Both of them at zero atomic percent bismuth. But you can see now with the change in the thickness, the one for the 120, the thinner film is 3.33 nanometers grain size, while the one for the 220 nanometer is 4.16 nanometer grain size. So this one simply tells us that grain size increases with increase in film thickness, and this is because the smaller grains, when you use a thicker film, the smaller grains agglomerate to form larger grains. Now, if you go back to our pictures, you'll see that there are no visible pinholes or cracks. So this means that it can make a good film for solar cell. Continuation of results. The XRD diffraction patterns for the 3 selected films revealed that they are amorphous in nature. Okay, our thin films are amorphous, and this is due to lack of long-range periodicity in amorphous materials. Okay, I've not shown the diffractogram here for that. Time was an issue and the connectivity issues. Now, the next one under results is the band gap energy. We discovered that the band gap energy decreased with increase in bismuth content. And this one can be attributed to the increased tailing of the valence band into the gap region. And at the same time, the band gap energy also decreased with increase in film thickness. And this was attributed to the increase in particle size and decrease in strain. Allow me to go to the slide where I have the diagram for band gap. You can see we have on the left-hand side a subtitle within the graph diagram. We have 2% bismuth. Then the right-hand side, we have 10% bismuth. Now, within the graph, we also have the thickness. The top one, on the graphs now, the graphs that have been plotted, the top blue, the blue one is representing the 220 nm thin film. The red one is representing 170. Sorry, it is 170, not 150. Sorry, I didn't see that. 170 nanometers. And the black one is representing 120 nanometers thin film. Now, if you look at these two diagrams, it's simply showing that the band gap decreases with increase in film thickness, because you can see the 220 nm for both the graphs. The 220 nm, which is the blue one at the top, is giving us a lower band gap. I had written a table. Yes, this is the table, the band gap energies. This is what was obtained from the graph. We have the 120 nm thin film. At 2% bismuth, it was 1.85 electron volts. 2%.
You now have 3 minutes remaining.
Sorry?
You now have 3 minutes remaining. Please proceed.
Okay, thank you. Sorry, so that is a summary of the information in the graphs. Allow me to comment on the transmittance. We also drew graphs of transmittance. And those graphs, we have 6 of them merged. It is because of the percentages. The first one is 0% bismuth, followed by 2, 4, 6, 8, and finally 10. And it is very clear that there is highest transmittance. The highest transmittance is within the wavelength region of around 650 to around 800 for all the films. So this means that the selenium bismuth thin film has a highest transmittance within that region. It is this implies that it is almost transparent. That's why it allows more light to pass through. At the same time, you can see the thin film, the thinnest, allow me to use that word, the thinnest film of the 3, the 120, is always giving the highest transmittance. So this one clearly indicates that transmittance increases with the decrease in film thickness. There was also a high absorption coefficient for all the films at all bismuth concentration. They recorded the high absorption coefficient of 10 to the power 4 in that order, to 10 to the power 5 for all. I've not displayed that graph here, but the lowest values of absorption coefficient were between the wavelengths 650 to 830 generally for all the films. Now, after we used these graphs of absorption coefficient against wavelength to obtain other values, which we used to plot the next graph, this one, to tell us how the thickness affects the absorption coefficient. And you can see the 220 nm thin film is showing the highest absorption coefficient at all bismuth concentration. You can see on the x-axis we have the bismuth concentration, all of them, but the 220 nm thin film has always shown the highest at all bismuth concentration. So this one simply tells us that the thicker the film, the higher the absorption coefficient. In conclusion, we say this, that this film, since it has been doped, it is not pure selenium, it has been doped. It has a lower degradation rate and can provide an overall low-cost material for solar cell technology to assist the common mwananchi. This research also ensures that we have good quality thin films. I had mentioned earlier that we have absence of pinholes and cracks in the AFM photographs. Then, we also discovered that the 220 nm thin film at 6% bismuth, if you look at the graph, this one, at 6%.
Time is up. Please conclude now.
Is at the highest. So it can make a very good material for a window layer in the solar cell. Thank you very much for your attention.
Thank you very much, Helen, for that well-articulated presentation. We are reserving questions to the last session. I noticed that the audience is not uploading these virtual presentations. Please, if you look under reactions, you can able to make a virtual upload by having those hands that indicate clapping. Thank you once again, Helen, for that presentation. We go to the next presentation. I'm told that Eva is now ready to present. Eva Shana?
I am ready to present. I'll be using Mr. Gilia's computer.
Please proceed. Can you please bring up your presentation? If you're going to presentation mode, and please start your presentation. Your time starts now. Your 15 minutes.
Do you see my presentation?
Yes, we can. Please proceed.
Okay. My name is Eva Tito Shana from University of Dar es Salaam. I'll be presenting on effect of sputtering power and film thickness schemes on electrical structure morphology and optical properties of molybdenum tri-layer back contact for first light film solar cells. It is one of our papers we are preparing with my supervisors, which are Dr. Mriuka and Dr. Samij. The outline of my presentation covers from introduction, materials and method, results and discussion, and acknowledgement. The interest of this work is based on investigating molybdenum film for thin film solar cells, which can be fabricated by using the configuration shown, which comprises your 4 layers from back contact, absorber layer, buffer layer, and window layer. And basically there is each material and each method used to deposit material for each layer. But the focus on this discussion will be on back contact, whereby a lot has been done on back contact and different material have been suggested to be used as back contact, example, niobium, platinum, all this material including molybdenum. But there are different properties needed for the best back contact, whereby the first one is high conductivity, high reflectance, and adherence to glass substrate. This is because the absorber layer is used to absorb all material entering the solar cell through the window layer. But for the light which is not absorbed in the absorber layer, when forced to the back contact, need to be reflected back to the absorber layer. That's why the back contact need to be of high reflectance and high conductivity. Together with that, the back contact also need to adhere well to glass substrate, which is another properties. But the investigation done more showed best properties compared to other material. Then it has been selected to be used as back contact. This is because molybdenum is chemically stable, and there is matching of thermal expansion of molybdenum and soda lime glass substrate. There is high conductivity and high reflectance, which does not degrade at high temperature. Also, it has high stability during fabrication, and it forms low resistive ohmic contact with the absorber. Best parameters can be obtained with mole back contact when the variation of different deposition parameters will be taken. This includes sputtering power, working gas pressure, substrate temperature, film thickness, and target to substrate distance. And today we are going to focus more on 3 parameters, which are sputtering power, working gas pressure, and film thickness. Also, there are a lot of challenges regarding to mole back contact. The first challenge, which is facing the single deposition of mole, it is difficult to obtain low resistivity and high optical reflectance simultaneously. And the other challenge facing mole back contact is peeling off of mole from glass substrate when thickness is greater than 500 nanometers. To address these challenges, material configuration have been suggested. The use of bilayers and tri-layers of molybdenum. The using of these materials means that the bottom layer can be deposited with different parameters compared to other layers. But in this way, bilayers has shown promising results compared to single layer, but still there were challenges of compromising resistivity and high reflectance together with the peeling off cases. Then tri-layer have been used recently, and a lot has been done in tri-layer, whereby other authors have been sandwiching mole oxide in between of bilayer to get tri-layers, and the others have been depositing more tri-layers with the same deposition condition, but to differentiate the deposition method like RF and DC. But in this way, you are going to focus more on depositing tri-layer under different condition, but by using direct current sputtering. So there is need still in tri-layer to compromise the conductivity and reflectance and to sort the peeling off cases. So this is study based on to compromise these parameters. And the potential parameters we are going to deal with are film thickness, working gas pressure, and sputtering power, whereby we are going to focus on their influence on electrical structure, morphology, and optical properties. To investigate the effect of film thickness, we had the 2 thickness schemes have been used. The first one called low, middle, medium, which means we have low bottom layer, medium middle layer, and large top layer. That is scheme 1. And scheme 2 with the large, medium, and low, which means we have larger bottom layer, medium middle layer, and low top layer. The choice of these thickness schemes was selected to investigate the problem of peeling off. And remember, all these layers shows different colors, which implies that each layer will be deposited with different parameters, such as working gas pressure, whereby bottom layer will be deposited at high working gas pressure, because at high working gas pressure, we're going to have a film with porous microstructure, but with better adhesion. And middle layer will be deposited at medium working gas pressure, whereby top layer will be deposited at low working gas pressure, whereby you're going to get compact microstructure with a low resistivity, which will give higher conductivity. And under these schemes, we had selected few samples, and in each sample, the first thickness will be for bottom, middle, and top layer. And for the second scheme, we had also selected these samples. And we have investigated this one at constant sputtering power. Then after obtaining the best sample in each scheme, the effect of sputtering power we investigated from appearance of samples. This slide shows the appearance of samples from each scheme, soon after deposition to 1 month after deposition, whereby scheme 1 of low, medium, and large shows the difference in appearance from day 2 to 1 month, whereby the molybdenum peeled off from glass substrate with the time. And the continuous peeling off is contributed by the variation of working gas pressure. Remember, I said we are going to deposit these top layers and bottom layer different working gas pressure, whereby we have tensile stress and compressive stress affecting the film, whereby it will affect the film with time. But at large, middle, low, you can see the film didn't peel off with the time. This is because the top layer top layer was seen and deposited at lower working gas pressure, while the bottom layer, which is thicker and adhesive to glass substrate, was deposited at high working gas pressure. And also we have investigated the influence of sputtering power after obtaining the best scheme, and you can see even from the image clearly that scheme 2 was the best choice for trial layer deposition of moly. Then effect of sputtering power were investigated using this scheme, whereby we have found that there is uniform grain distribution using semi and AF images, and also increase in grain sizes and surface roughness. And this will explain the variation on electrical and optical properties. So we have observed from the images, we have uniform grain distribution, increase of grain size, and increase of surface roughness, which is contributed by the sputtering power, which as the sputtering power increases, it will of course the merge and the quantity of grains, which result in bigger grains and in surface roughness. The effect of sputtering power on conductivity. Remember we had two schemes, so the pink line shows the best scheme for scheme 1, which was investigated at different powers, and the blue one shows for scheme 2, whereby you can see there is slight variation from the two schemes, but still scheme 1 shows the better trend. And this is because of the thickness of top layer, which is deposited at low working gas pressure, compared to the thickness of top layer of scheme 2 deposited at the same low working gas pressure. And this can be caused by the changes of sputtering rate with the sputtering power, grain size, and you can see from the X-ray pattern of moly, it shows at this power you have a strong peak which reveals better crystallinity of the film at that deposited power. The influence of sputtering power on optical properties also is shown in this slide, whereby we have for 100 to 250 watt, and it shows with the increase of sputtering power, show also the reflectancy increases, and that can be also attributed by the compactness of the films with the sputtering power and the changes on microstructure, which is shown by AFM on the same image. And this shows the average reflectance calculated from the graph 1, and it shows that at this power we have relatively increasing average reflectance. Also, the influence of film thickness, this is for scheme 1, and the graph 2 is for scheme 2, and it shows there is a variation with the thicknesses. The first sample of 200, 300, and 500 nanometers shows higher conductivity compared to other samples. And for scheme 2, the second sample of 600, 250, 150 also shows the higher conductivity. There is no clear trend on variation of graphs, but the reported values of conductivity in this working is slightly higher compared to the reported values by other authors. And this variation is contributed by the thickness of top layer, which is deposited at lower working gas pressure. So working gas pressure has the major effect on electrical properties. So it depends the working gas pressure selected to deposit the top layer. On optical properties, also the film thickness has effect, whereby it can be shown that this selection of 600 to 5150 nanometers showed better optical reflectance and average optical reflectance compared to others, and that has been shown also from the microstructure of this specific film, contributed by working gas pressure, which affect the compactness at low working gas pressure and the grain sizes. And so what was done in this work basically was to investigate the thickness schemes, whereby you have seen the scheme 2, which is large, medium, low, will be the best scheme for depositing to a layer of molybdenum at DC using DC sputtering. And also we have investigated the variation of sputtering power, and you have seen the power greater than 150 watt will be the best choice to deposit tri-layer films. The challenges it addresses with the peeling off cases, whereby you have seen the best scheme to use to avoid peeling off. And if the scheme will be used the other way around, the film will peel off, and have seen why. And the other challenges we have addressed in this work, we have succeeded to compromise the resistivity and reflectance. That's why that means you can get high conductivity and high optical reflectance simultaneously depositing mold. I acknowledge trust ISP, my supervisors, Msseesa and Solar Energy Group. Thank you so much.
Yes.
Chair, you are muted. Chair, you are muted.
Yes, saying that please let us upload the well-articulated presentation by Ms. Eva Shawa. Please hold your questions. We'll be going to the discussions and questions in the final. We now have Judith. You ready? Judith from University of Eldoret.
Yes, I'm ready.
Okay, please show us bring up your slides.
Okay, thank you, Chair. Welcome, ladies and gentlemen, to a presentation on dielectric impedance spectroscopic studies of niobium-doped titanium dioxide thin films. I'm Judith Chebogen from University of Eldoret, together with my supervisors, Dr. Mkirema Maganga from Kabarak University and Mgendi Mwamburi from University of Eldoret. Now, the outline of the presentation is as shown on our screens. I hope we can see the screen. Share. Hello.
Yes, we can see you. Continue.
Okay, so that is the outline of this presentation. And what motivated this work is the applications of titanium dioxide, which is currently applied in or is used in varied applications, for example, in the food and drug industries as a colorant, and in inks and paints, in ceramics, in cosmetics, as a sunscreen component, also used in photovoltaics to design dye-sensitized solar cells, also as a photocatalyst, used in self-cleaning surfaces and as a photoremediation catalyst. Now, in the near future, there has been an increase in demand for insulators with high dielectric constants in different applications.
Judith, we can't hear you.
Judith? Judith, can you check your audio? Judith, I think your microphone is off.
Hello?
Yes, please. I think we're not hearing you. Judith, can you hear us? Judith, can you hear us? Judith, are you in a centralized place? Professor Mabora?
Chair, I don't see Judith in the.
She's gone
as
off?
a participant. I don't know what has happened. I think so. We suspect maybe power or a gadget. So I'm suggesting that maybe we can take questions and answers for the ones who have presented, and then we can. Oh, is there another presenter again?
Unless Sam Njungu has come.
Presenter.
No, that was the last one.
No, Njogu was said he's not presenting.
Yes, so Judith was going to be the last one to present.
Njogu is not presenting.
Okay, so that means we'll be going into the question.
Okay, so I suggest maybe and answers.
We'll go to
if
questions,
she comes, she can continue presenting.
Yeah, so if she comes in time, then we can go back to the presentation. Okay, we have questions to I think the two presenters. Questions? Please, as usual,
yes, please.
Yourself. Yes, please.
Yeah, my name is Professor Samir. I'm from the Technical University of Kenya, domiciled in the School of Electrical and Electronic Engineering. And to me, I found the presentations very good. A lot of investigative research has been done. But what hits me most is the lack of validation of results. You know, I know when you do experimental research, you increase the percentage of bismuth, you reduce the band gap. Of course, those are things that you see in the experimental world. But how does it compare with what others have done? Because we can't be taking ownership in that context, you know. So if the presenters can kindly explain how does it fare with what others have done in the context of percent differences, because I hear many answers that say far off and things like that. That's very ambiguous. We need to have some percent differences and so forth. Thank you.
Thank you very much. I think that's a general comment to all the presenters. Other questions or comments? Is that a question?
Am I audible enough?
Yes, please. Please go ahead.
This is Odari Victor from Masinde Muliro University. I want to appreciate Eva Tito Shana for her good presentation, but I have a few questions for her. I can see she's working on the casterite thin film solar cells. Structure is, if possible, she can display the structure of her cell.
Eva, did you get, please? Okay.
Okay, please proceed to the structure of your cell. That should be in the introduction. I think the third slide. Good, thank you. So, as you have displayed, you are working on molybdenum, which is a back contact.
I think you're showing us the last slide.
My question is this. Molybdenum in most cases is used as a whole transport layer in solar cells. And that means it should have very low or small thickness to allow charges to pass through. But I can see you are working on bilayer and tri-layer of molybdenum oxide. So I wish to know the thickness range in which you are working with.
I don't
I
get
hope,
your question. Can you repeat, please?
Could you repeat your question?
Well, I said
And
molybdenum is a
Tusemi,
P-type
can you please
material.
switch off your mic? Tusemi, please turn off your mic. Dr. Dara, please proceed.
So molybdenum is a P-type material, and in most solar cells, it is used as a whole transport layer that simply allows the P-type charges to pass through. So in your case, you are using it as a back contact. What is the range of thickness that you're working with, given that you're working with bilayer and trilayer, and in most cases it is used as a whole transport material, which normally requires thickness of roughly 30 nanometers.
Okay, thank you for your question, Dr. Dari. As I have said, I'm working on back contact, whereby I am using molybdenum as a back contact, and the range of thickness I'm using 1,000 nanometers. As you can see, I have 3 layers. If you totalize the total thickness, you get to 1 micrometer thickness. And others are using from 500 to 1 micrometer, and I'm using the range of 1 micrometer, and I am working only on tri-layers. I've explained what others have done on single, bilayer, and tri-layer. Thank you.
Thank you very much.
So my concern is that that thickness range may be. Can I proceed?
Yes, please proceed.
Yes.
So my concern is that thickness range may be too large for the contact layer, and that will lead to loss of charges from the cell or from the absorber layer, which will lead to low efficiencies of the cells. So kindly check on that. That is my concern.
Okay, thank you.
Okay, noted. I'm now informed that Judith is able to present. So we'll suspend our question and discussion session so that Judith can present. So perhaps we are not sure where you stopped. Is that where you stopped?
I can move back.
Just move a bit back so that maybe people have lost you much earlier.
Okay, so as talking about the motivation of this work, that we are looking at the applications of titanium dioxide in the current life, that we use it in different applications, including what I had mentioned in photocatalysis and the rest. Now we said that there is an increase in demand for high dielectric constant insulators to be used in high density dynamic memory applications, where titanium dioxide has promised to be one of the candidates that can be used to replace silicon oxide. Besides that, it is also environmentally friendly and can be used in the design of smart windows. And therefore, we thought we could use titanium dioxide, or we could study titanium dioxide as for it to be applied in those different applications. Now, we did impedance spectroscopy, which gives an opportunity for us to explore the electrical behavior of a sample as a function of alternating current with a variable frequency. We want to see how it behaves to an electric current, to alternating current. And as we do that, this is normally done by studying the exchange interactions between the current and the sample at different sections. We have inside the grains, at the grain boundaries, and at the surface of the electrodes. Now, this can be modeled by use of this circuit here, or this setup that we have here, where to model the grain itself, we can use a parallel connection of a capacitor and a resistor. To study grain boundaries, we can also use a parallel connection, a parallel circuit where we have a capacitor and a resistor. And to study the surface of the electrodes, the interaction at the surface of the electrodes, we could use a capacitor or even a resistor, but that is how that can be done. So we've said that to study the electrical behavior, you can simulate using a suitable combination of a resistor and capacitor circuit. Now, in the experiment, niobium doped thin films were deposited on unheated glass substrates using DC magnetron sputtering, followed by heat treatment in air for 30 minutes at 500 degrees Celsius. Two targets were used, that's niobium and titanium, and this was done in argon and oxygen atmospheres. To get different concentrations of niobium, the target power, that is niobium target power, was varied between 20 watts to 80 watts. After that, the films were characterized so that you could be able to get the impedance measurements. That was done using the broadband, the Novo Control broadband dielectric converter, the Solartron frequency response analyzer, and the frequency range that was used was 10 raised to power -2 to about 10 raised to power 7. Again, we studied the structure using X-ray diffraction, and the composition of the films was done using Rutherford backscattering. Then the thickness of the films were also studied using the alpha step profilometer. The film was the setup of that film was as shown, where we have the glass substrate here, we have the film, and some gold contacts were also spattered here on the surface of the film to aid in the measurement of impedance for impedance measurements. Now, in the results, this is what was observed, or this is what was found, that the RBS showed that there was niobium in all the films, with the highest concentration of niobium inside the titanium dioxide films being 8.5 atomic percent, and the least being 0.5 atomic percent of niobium. This was done by using the geometry that is seen here for Rutherford backscattering, where we have a stream of ions that are directed towards the film, and the backscattered, the energy of the backscattered beam is measured, and then you can be able to get the mass of the sample, and therefore we got this picture here showing the amounts or the doping concentrations of niobium in the titanium dioxide films. In the dielectric properties, we found out that the impedance that were obtained from the broadband dielectric converter that we used to measure the impedance, we saw that the undoped film, that is the one in black here, had the highest impedance. We know that titanium dioxide is a semiconductor, so it has a higher impedance because we do not have any free carriers. But once we dope with niobium, you introduce some free carriers in the semiconductor, and we expect that the impedance reduces. That is what happened here for 0.45 atomic percent of niobium, the impedance decreased on doping. But an observation that is seen here is that at 3.59 atomic percent of niobium, the impedance is very low. But as you increase the dopant within the sample, you see that also impedance starts increasing. That is what is shown in the second figure, where we have impedance and atomic percent of niobium. That 3.59% atomic percent of niobium had the lowest impedance, while at higher doping levels, the impedance started increasing. This was attributed to a possible segregation of the niobium atoms at the grain boundaries in titanium, which upon heating or annealing in air, this niobium reacted with oxygen to form niobium oxide, and niobium oxide layer within the grain boundaries, and hence raised the impedance in the films. Then wanted to check the grain boundary effects on impedance, and we found, and that was done by fitting the impedance data that was obtained using the serial layer model that is shown here, where SER here shows the series resistance, that is between the gold contacts that we had seen in the circuit or in the figure. Then the first part where we have R1 and C1 is the part that will model the effects at the grain, while R2 and C2 will model the impedance, or will give the impedance at the grain boundaries. So when this was done, when the modeling was done using the MEISP software, the following, the impedance data was fitted using the software, and once a good fit was obtained, a good fit of the impedance was obtained, some model parameters were read from the software, and it was observed that the film that had 3.59 atomic percent of niobium had capacitance 2 being 3.44, or C2 was seen to increase from 3.44 picofarads to about 135 picofarads, while C1, that is at the grain, the capacitance reduced from 5.41 picofarads to about 1.74. That means the increase in capacitance here that we see is majorly attributed to the impedance at the grain boundaries, because remember we said the second part of the circuit where we had R2 and C2 was to show the impedance at the grain boundaries, and R1, C1 was to show the impedance at the grain and within the sample itself. So at the grain boundaries, we had a higher impedance, and that means that is what really affected, that is what had the effect on, or that is what brought the effect on the impedance of the sample. Again, we looked at the dielectric permittivity of the different samples, and we found out that for the undoped sample, the dielectric permittivity was low at low frequencies, but increased at high frequencies. But for the doped samples, the dielectric permittivity was high at low frequencies, then decreased as the frequency increased, and then became constant after some frequency. Now, when we look at the 3.59 atomic percent niobium here, the frequency is the dielectric permittivity is so high. Why? Because the impedance is low. This is again related to what we had seen before, that the impedance as shown from the converter was low for 3.59. This again is seen here in the dielectric permittivity, that the dielectric permittivity at 3.59 is very high compared to the other films, in as much as they have the same behavior. The doped films have the same behavior. 3.59 atomic percent niobium had a high dielectric permittivity at low frequencies. Then again, in the dielectric loss, the undoped film behaved differently. Just as seen in dielectric permittivity, it has almost the same graph as what we saw in dielectric permittivity. And the doped films also have got the same nature of graph as seen in dielectric
You have now 3 minutes, Judith. 3 minutes remaining.
So dielectric loss here is also high at the 3.59%. Why? Because it has a low impedance. We have more charges flow, and therefore we'll have a higher dielectric loss. Now we said that since the dielectric loss here is low at high frequencies, then we saw that doped films are suitable for high frequency applications. Why? Because we have a low dielectric loss at higher frequencies in the doped films. So we conclude by saying that the effects of dielectric properties revealed that there is a drop in impedance for low levels of doping, but higher levels of dopings led to increase in impedance, which we attributed to the incorporation of niobium oxide in the grain boundaries. Then grain boundaries are actually the ones that contributed remarkably to the dielectric properties of the films. Thank you so much.
Thank you very much once again, Judith, for that wonderful presentation. I think we have got some time. We invite questions for both, first to the most recent presentation. Questions? Comments?
Through the chair.
Yes, please go ahead.
I have a question for Judith. First of all, that was a good presentation. I appreciate. But if you go to slide number 8, if she's able to project
show us your
slide
slides.
number 8.
Yes.
Please proceed to slide number 8, where we have the circuit. And your spectra. Good, that one.
Yes.
So from the spectra,
Mm.
yes. From the spectra, I can see you have a single semicircle.
Yes.
In my understanding on how to come up with a circuit for that, is that every RC circuit that are in parallel produces a semicircle. Like if you look at your circuit, you have two semicircles. So you have two RC parallel connections joined together. So in my view, I should be expecting to see two semicircles in your spectra, where each semicircle is represented by an RC. So how did you come up with this circuit? I may be right, I may be wrong, but give me your opinion on how you came up with this circuit for the spectrum.
Okay, thank you, Victor, for that observation. Allow me to kindly request Dr. Maganga to respond about the same.
Okay. Okay, thank you very much, Judy, for presenting in a very eloquent manner. So that was good. Now for a single RC combination, you get a perfect semicircle. A perfect semicircle, but this is not a perfect semicircle. It's an extended semicircle. So there are two. It's actually a combination of two semicircles. So it's a superposition of two. If you use one, you'll never get anything. In fact, even the circuit, if you check on the right, the semicircle is not even a perfect fit, meaning there should be some additional element, but this was the closest fit. So for one, it doesn't fit. For a single RC combination, doesn't fit. It's an extended one. Okay, thank you very much. Unless if there's a follow-up question. Any other questions, comments? either on the most recent or the ones that we had just that had just been presented. You have a question? Christopher, switch off your mic, please. Dr. Maganga, switch off your mic. Thank you. Any other questions, comments? So,
my comment has not been answered regarding the validation of results, please.
Oh, sorry. This was to. Can you just remind us? Was it a general question or specific to a presenter?
It's a specific question for all the three to provide some validation to their work.
Okay. So the presenters, the question is to all of you. Anyone can start. Eva, do you have a comment or answer to that question? Eva Shana?
Can I help the students?
Yes, please, go ahead.
Yes, I think that is advice from Professor Hamia about validation of results, because he has seen that most of the students are just presenting the experimental work without validation. So I think what he wants is the students to prepare to compare their results with other works. I think that's what Prof wants. So if the students have not done that, please go back to your work. Make sure you compare your work with other works, and then you comment. So I think that's a good point from Prof. Prof. Hamia, can you add more?
Hello?
Yes, I do agree with you, sir. Thank you.
Hello?
I have a comment on that.
Okay.
My work, my results are compared to what others have done, especially on trials, and that is included in my dissertation and in my paper. I didn't include this in today's presentation, but it is validated in comparison with what others have done.
Okay, thank you very much. Any other comments, questions?
Hello?
Yes,
Hello?
yes, please.
I just wanted to say that usually in the presentation, you don't present the validation, but in the document, when you have done your work, definitely you do the comparison initially in the literature review and when you are doing the analysis. But for the presentation for the seminar,
I think that's not a very good answer, because in a presentation, whenever you produce results, it's always good to show some comparison. That's all I'm asking, because you can't show analysis of results and claim ownership. There has to be a % tolerance with what others have done. It's very, very important. Otherwise, what's the use of presenting results and you don't validate it? It's extremely important. And you don't say it's in my thesis, or it has compared well by how much, by what percentage. So we have to be very, we have to remove the ambiguities. This is just a constructive suggestion, please. Please take it in a constructive manner. Thank you.
Thank you, Prof. I agree with you that I think it's not good to have to assume that the listeners understand what you have done, and that somewhere at the back in the drawer, you've actually done that work. I think it's important to present the results that you have and be able to make comparisons, as Professor Hamia has indicated. Any other comments, questions? I'm thinking we've done well on time. Professor Mabora, I think maybe I should hand over back to you.
Yeah, thank you very much, Chair, Dr. Msseesa and Dr. Waita, for managing that session. You'll continue again from 2 to 3, because this session was a bit long. There are many presentations. So you'll continue from 2 to 3.
Okay. I think we agreed that Professor.
Yes, yeah, that's
yes, please.
That's as per the program, but we can discuss.
Oh, the program,
you're
yes,
not
yes, we
available.
did.
Maybe
Yes,
someone
indeed.
else.
Okay.
Yes. Yeah, yeah.
Okay, thank you very much.
Yeah, and then after your session, which goes up to 3, the other session will be chaired by Dr. Sylvester Hatwambo, and the rapporteur will be Dr. Maganga. So just prepare for that. Hatwambo, I think he's back. He had challenges in the morning of power, so he's back. So we have saved some time, but not much. So I suggest that we break for lunch and we come back at exactly 1:55 so that the program starts at 2. So we can break for lunch. Enjoy your lunch break. Thank you.